In this video, I'm going to show you how to fit a subsampling model for most data sets, and it really just requires an additional random term that you have to specify inside Proc Mixed. So in this video, I'll show you how to do it in um, in SAS. In a later video, I'll show you how to do it in Jump. So this is the model that we want to try to fit. Again, with subsampling, we have a certain number of replicates for each treatment, and then within each experimental unit, we have additional subsamples, 1 to, let's say, n sub ij. So for the most part, we're going to be focusing on cases where we have equal replication for the treatments and then equal number of subsamples for each of the experimental units. So same number of observational units is the same thing. So we need to specify a model then that has two random terms, one for each experimental unit and one for each observational unit. So the very last error term, that's a residual error term. In a lot of cases, you don't need to specify that in your model yourself, but you do need to specify any other random effects that aren't as fine as, when I say fine, I mean there's always a residual error term for each individual observation, but here we have an error term associated with multiple observations. So I need to figure out a way to specify a random effect term for each experimental unit. And so this is going to require us to change how we structure our data set and how we fit our model. So I have a paper towel experiment where there's 8 different treatments, and we do 3 replicates per treatment and then 3 observational units per experimental unit or per replicate. So this is the file. This is where it's located in my data set. So I filled that in the proc import code where it's located. And I'm going to call that data set PT for paper towel. So just highlight this and click run. So the log says it was successfully created. These are data sets that we're going to create in this video. Here's that PT data set. So let's just take a quick look at it. So here I have my treatment column. Treatment 1, 2, 3, goes all the way down to 8. Here's how I'm measuring the paper towel. This is measuring the strength of a paper towel after I apply some treatment to it. So it's a combination of, for example, what I'm putting on it, whether it's, I think the example is water or beer. We'll come back to this example when we talk about factorial experiments, but for right now I'm just saying we have 8 treatments. So you need to add one of these 2 columns in order to do subsampling. So we need to indicate how these observations are grouped together. One way to do it is to indicate which experimental unit it corresponds to. So this is experimental unit 1. These are 3 subsamples for that unit. This is experimental unit 2. These are the 3 subsamples for that one, and so on and so forth. So as long as they're different numbers or different indicators for what experimental unit you're working with, you could do it that way. Another way is to indicate the individual replicates, and this is kind of a way to more match the model as it's written. So here I have EIJ, so my replicate is going to be my J index. So either way is going to work. I'm going to use the experimental unit code, experimental unit part, and then at the end show you how you can use the replicate part. So this is how my data looks. Before I show you how to do it in Proc Mixed, let's just do some calculations to make sure that what we calculate is actually done correctly. So I can actually do the sums of squares myself using the formulas that are given in this PowerPoint. So I know this is how I calculate sums of squares. I can actually do this manually in SAS. And I'm just providing code to show you how you can do that. So again, the model or treatment source of variation, this is comparing each treatment mean to the overall mean, squaring it, adding them up over treatments, and then multiplying it by n times r. Experimental error, this takes each experimental unit mean and subtracts it from each treatment mean, adds them all up, and then multiplies it by n. And observational error takes each individual observation and compares it to its respective experimental unit mean, adds them all up. So I can do that manually using proc means in SAS. So first I'm going to take averages over subsamples. This is what that code does. And so what I'm going to be doing here is I'm going to be taking the mean for each experimental unit, and I'm also going to be doing the variance across each experimental unit. So each variance I'm going to get will be the variance of my observational units within each experimental unit. So let me just run this to show you what I mean. So this is going to create a data set called EU means. Let me open that up. So this column right here where it says variance, it's going to be the variance. This is the 3 observational units that were in the first experimental unit. And then this is the variance of the next one and the next one and the next one. And so what I want to do to get my observational error is I want to average all of these things together. And that should give me my experiment or my observational unit estimate. So let me just take the average of those, and it's going to print those out, and I get 13625. So this is what my MS observed should be when I do my analysis. Okay, let's scroll down now, and now I'm going to be doing the same thing for MSE. So I'm going to be doing the averages, or doing the variance for each treatment using the EU means from this data set up here. So this is going to create my yij.bars, and now I want to do the variance of those yij.bars with respect to each treatment. Just to show you again, these are my EU means, and I'm doing them with respect to these individual treatment means. That's what that by treatment option is doing. So it's almost the same calculation as before, but I have to use the experimental unit means instead. And so let me take the average of those variances. Now this is going to give me part of MSE because I still need to multiply it by my number of subsamples, which in this case is 3. So let me run this. So this is almost my mean squared error. I need to multiply it by 3 for it to actually be my mean squared error. And so I don't need to do that with any code. I'll just do it manually. So if I multiply this by 3, this should be my mean squared error, 271,952. Now if I want to get an estimate of my sigma squared experimental error, sigma squared E, I need to take MSE, subtract MS observed, and divide it by my number of subsamples, 3. And so this is what this code is going to do, and it's going to put the answer in the log. So when I get an estimate of sigma squared E, which we're going to see in the Proc Mixed code I'll show you, I should get 86,109 for my estimate of sigma squared E if everything works correctly. Luckily, it's not negative like we saw as a possibility in class. Now, just to get an estimate of mean squared treatment, I'm going to take the variance of my treatment means, and then I have to multiply those by the number of subsamples and the number of replicates, which are both 3 in this case. And so my mean squared treatment this almost calculates mean squared treatment, 342,775, but again I have to multiply it by R and N. And that's what this code is doing. And if I go to my log, my mean squared treatment should be 3,084,975. So these are the numbers that we should expect to see if my Proc Mixed code is running correctly. All right, so now let's look at the Proc Mixed code. So here's how the Proc Mixed code looks with subsampling. The only thing I've added from before is this method equals type 3 possibility and this random statement right here where we're going to be using to define our experimental unit effects. So for right now, we'll leave this method equals type 3 commented out, so it's not actually going to do it. So data equals PT. So if I'm not using type 3 sums of squares, what is SAS doing? Well, what it's doing in the background is it's doing a REML, or let me spell that out. REML, or restricted maximum likelihood method. So this method is actually an automated method for SAS to kind of figure out how to estimate your fixed effects and your random effects. So it's kind of like doing sums of squares, but not quite. But when we have nice balanced data, like we have in this example, the REML method and the type 3 method will actually be exactly the same. So the REML method isn't necessarily based off of sums of squares, but in a lot of cases it will reduce down to a sums of squares approach. So in my class, I need to specify what are my classification variables. So this is going to be both treatment and experimental unit, those two variables in my data set. My model is going to be strength equals treatment, because that's what my response was. Let's just make this consistent. Let me do this TRT. Now I don't put experimental unit in my model statement because it's not a fixed effect. It's a random effect. So in order for me to do that, I need to write it after random. And so I'm just going to put EU. So what this should do is I'm going to be fitting a random effect model with, let's go back up to our model, with this fixed effects part, this additional random part, and then this residual error term, which is always added towards the end. So each one of these corresponds to my experimental unit, and I'm using that as my random effect, and so I should have these effects coincide with each other. So I'm specifying my model correctly in this case. For now, let's ignore these LS means and this contrast and this estimate part, so I'll just comment those out just to see how well this works. So let me run this code, and I get this output. So my let's go through this output real fast. So here it says REML estimation method has all the kind of information here. This degree of freedom method is going to be something we'll talk about in just 1 second, because you'll see the test isn't quite working the way we want it to. So the first thing that we want to look at is this covariance parameter estimate. So this is our estimate of sigma squared E and sigma squared E star, not sigma, but sigma squared. So here's that 86109 we saw before, what our estimate of sigma squared E should be. And this was our MS observed 13625. So this method seems to be working, at least in terms of estimating our variance components. If I look at my type 3 tests of fixed effects, I see that I have 48 denominator degrees of freedom, which in this case, let's make sure that those are actually the correct number of degrees of freedom. I know the numerator degrees of freedom are correct, but what about my denominator degrees of freedom? So my denominator degrees of freedom for this example, let's just use this as kind of like a work table, not proc import, proc mix, here we go. So my denominator degrees of freedom should be T times R minus 1. So T in this case is 8 and R minus 1 is 2, but that's 16. So that should be my denominator degrees of freedom. So it doesn't look like this test is using the correct number of degrees of freedom. So while it's doing the correct estimation, this is not doing the correct test. And so the problem is in how REML decides to calculate degrees of freedom. So you can go in the documentation to see how it works, but SAS doesn't really know how to calculate the degrees of freedom correctly, at least for the REML method. So one way to fix this is to specify another way for it to calculate degrees of freedom. So I can use / denominator degrees of freedom method, so DDFM. And one thing is I can type it in as KR, which stands for Kenward-Rogers correction. So now let me rerun this with this other degrees of freedom calculation method, and there are my 16 degrees of freedom. So notice my F value didn't change, just my denominator degrees of freedom. And so this is the correct test to use. So this was the same, this is the same, and this is how I could correctly do my denominator degrees of freedom. But let's check those sums of squares, because that's how we originally checked this. So if I don't want to use REML, if I want to use the sums of squares method, I want to uncomment this out, method equals type 3. And so there are some restrictions. For example, I can't use the Kenward-Rogers technique for this case. So let me use method equals type 3 in this case, and hopefully this will work, but as we will see, it does not. So when I do method equals type 3, I get output that's a little bit different. So there's my issue with the type 3 fixed effects again. There's 48 denominator degrees of freedom. But I get an additional table up top that actually gives me expected mean squareds and things like that. But unfortunately, you'll notice that the treatment part of this table is totally wrong. It says there's 0. So again, this is a problem with how Proc GLM calculates sums of squares, some of the notation it needs to know how to calculate these things. So I think the problem is it doesn't know how to separate the treatment and the experimental unit sums of squares, because we haven't told SAS that these units are sort of nested inside of our treatment. So in order for me to calculate this correctly, and this is actually the way you should be calculating or doing subsampling in most cases, is you need to tell SAS that these units are nested inside the treatments. So the way you do that is you do EU, and then in parentheses you tell it what it's nested inside. So I'm going to put treatment nested inside experimental unit. And this is the way I'm going to be able to tell SAS to calculate these things correctly. So let me run that. So there's my denominator degrees of freedom. That's fixed, or that's been adjusted correctly, not fixed. Here are those sums of squares. Here's a number that we saw before. Here's a number that we saw before. And here's a number that we saw before. These are the right error degrees of freedom. So this part right here is is the same test as what I got down here. And this right here, this is testing for whether sigma squared E is bigger than sigma squared E star. And we can see that it is also rejected in that case. So once you have this set up correctly, you can use LS means, contrast, and estimate to do all the same things that you had done before. So I won't go into that because it's the same syntax as everything. It's really just showing you how to define the error term correctly. We could have also used the other column in this data set, rep. But in this case, if I change this to, let's say, rep, and this to rep, and I use, let's say for right now, let's go back to REML, this is actually not going to work at all. And the reason is because we're not telling SAS in any way that rep 1 here is different than rep 1 here. So it's going to kind of average all these reps across each other, and that's just nonsense. It's just not doing anything correctly. So let's highlight this. I have 62 denominator degrees of freedom. These estimates are way off, and so the reason is it thinks that rep is actually, it's actually treating rep as almost a block in this case, which is just not the right way to do it. So this thinks there's just 3 replicates when there should actually be much, much more than that. So this further emphasizes that we need to tell SAS that these things are nested inside of treatment. So not even doing the degrees of freedom method would fix this problem. Instead, we need to do rep nested inside treatment. And so here we see now this is correct. These are what we had before. And the same thing is true if we start to use that method equals type 3 again. So there's my table back, and this is what we need. So this is actually kind of cool because it gives you the expected mean squareds. And this Q treatment means we have some quadratic form of treatment. So it doesn't exactly tell you. I think you have to run this in Proc GLM for it to actually show you what this expression is, but it's helpful just to kind of make sure that the tests are done correctly, and it tells you actually what the tests are being done when you compare the expected mean squareds. So I will say method equals type 3. There are some additional options you can put inside Proc Mixed that'll make type 3 unavailable, but when you have something simple, some code like this, type 3, you can use that, and it's nice because you can actually calculate some of these sums of squares yourself. In a minute, I'm going to show you how to do this nested sort of effect in JUMP, which should be a short video because I've explained why you need it in this case.